Hello, everyone, and welcome to today's webinar, DER Solutions Enabling Interoperable SCADA Communications for PV Inverters through Embedded Controllers. My name is Beth Capellas, and I'm the Marketing Manager here at Triangle MicroWorks. Before we get started, I'd like to go over some housekeeping items and some introductions. The webinar is scheduled to be 1 hour long. We will be stopping for questions a couple of times throughout the webinar, and we'll stay on afterwards to answer as many questions as possible. The audience is on mute, so please submit your questions online using the webinar tool under the section titled Questions. We will try to answer questions online during the webinar, and we'll read and answer questions during the breaks and at the end. Next, I'd like to introduce our speakers. We have two folks with us today from National Renewable Energy Lab, also known as NREL. First, we have Kumar Prakabar, who is a senior research engineer. He leads research projects targeting improvements in distribution system protections and interoperability of distribution system assets. He's a technical contributor in multiple microgrid controller evaluation projects and advanced distribution management system evaluation projects. We also have with us DP Vigamintan, who is a research engineer at NREL with a focus on energy system integration and grid modeling and simulation and performance optimization for scientific software. Lastly, we have our own Joel Green from Triangle MicroWorks. Joel has worked with communication protocols for over 20 years, with the last 10 years in the power industry. He is the lead engineer for 61850 development and products at Triangle MicroWorks and is heavily involved with 61850 industry groups. He also works as the co-editor of 61850 7-2. He is a member of the UCA Test Committee and Test Procedures Working Group and involved in IEEE Standard Association. So now that you know everyone, I'd like to give you a little bit of background on Triangle MicroWorks before we get started. We were established in 1994 and headquartered in Raleigh, North Carolina. We have customers in 70 countries and work mostly with equipment manufacturers, electric utilities, and system integrators. The products we offer all support standard SCADA protocols and fall into 3 categories. The first category is source code libraries. We license source code directly to manufacturers for use in their devices and systems. This allows for a much faster time to market. It greatly reduces their costs and their development time. We also provide testing tools supporting these libraries and protocols. These tools are used for communication testing in the lab and the field. They are designed to troubleshoot, simulate, and automate testing. Lastly, we also provide a SCADA data gateway supported on both Linux and Windows for protocol translation and data concentration with standard SCADA protocols as well as OPC. We are heavily involved in the standards committee that supports SCADA protocol, like UCA Group for 61850 and DMP user group and technical committees. Through our participation, we help define the protocols, stay up to date on the changes that take place, and ultimately provide feedback based on our customers' needs as the protocols continue to evolve. So now that you know a little bit more about Triangle, I would like to go ahead and hand it over to Kumar, who's going to kick off the topic that we're here to learn more about. So Kumar, I'm going to go ahead and make you the presenter.
Thank you, Beth. Let me see if I can share my screen.
You should have control of the screen now.
Can you see my slide?
We're not seeing your slide, we're seeing your window screen.
Oh, then let me move my project here. Okay. Can you see my screen now?
Yes. Yep, we're seeing it.
Okay. Double checking one more time so you can see my screen, right?
Yep, we can see it. You're good to go.
Awesome, thank you. So yeah, hello everyone. This is Kumar Prabhakar from National Renewable Energy Lab, and we're going to present primarily on a couple of projects. The work came out of a couple of projects. The first one is additively manufactured PV inverter, and the second one is technology commercialization funded project, which is enabling interoperable SCADA comms for PV inverters. Both of them are funded by DOE, Solar Energy Technology Office, and we have cost share from Triangle MicroWorks for the second work. So for the contents today, first I'll talk about the smart PV inverter control capabilities, a little bit of background on the protocols, the interoperable protocols that we have chosen to use here, and the steps that are involved in enabling this interoperability protocols, and also background on the software tools that we used to achieve this, and then the ICD file design, which is a critical component in the interoperability, enabling interoperability on the microcontroller, and finally a demonstration of data exchange between a client and the server using a real-life microcontroller board. So first, I want to give some background on NREL and the type of work that we do. So I work primarily in the Energy Systems Integration Facility. ESIF is a national user facility located in Golden, Colorado. We call this a user facility because the primary goal behind our facility is to enable resources for researchers and engineers around the world that focus on renewable energy integration into the grid. So we have calls every year. I think it's now called as a ARES user call, where anyone in the world can ask for resources, high performance computational resources or lab resources to help with any renewable energy integration challenges. So primarily the work that I do is based on controller and power hardware in the loop. We do have megawatt scale power hardware in the loop capability. We can go all the way up to 2 megawatts on the DC, 2 megawatts on AC, and the lowest we can go is a few kilowatts. And we also have multiple controller hardware in the loop capabilities, including multiple digital real-time simulators that we can use, microcontrollers, high-performance computational facility, and most relays and protection devices for CHIL. For the work we're presenting today, we're focusing on interoperability for PV inverter. So the slide that I'm showing, it shows the smart inverter controls that we built few years ago and built additively manufactured PV inverter in the lab. So we took the smart inverter capabilities that we built for this inverter, specifically volt-var, volt-watt, frequency watt, and then other controllable things like ramp rate and voltage and frequency right through, and try to enable interoperability and allowing clients like a microgrid controller or ADMS to talk to the inverter and change these settings in real time. So these are the curves that we used originally in the paper for the 3 different settings, and also the right through settings borrowed from Hawaiian Electric Company. And this was in 2017. So we used data from probably 2016 or 2015 on this work. Since we did this work, a lot of things have changed in 1547 and UL standards, and it's always evolving. But the fundamental is still the same. Basically, these are curves, X, Y curve points, regardless of the volt-var, volt-watt, or frequency watt, or even the right-through settings. So in this demo, we'll show how you can update these X, Y curve points to an interoperable communication from a client to a server. And I'll hand it off to Joe for the presentation.
Okay, Joel, I'm going to make you a presenter.
All right. Good morning, good afternoon, good evening. This is Joel Green with Triangle. And
okay, Joel, your
there comes my screen. I'm going to tell you a little bit about the background of 61850 standard that's used in this project. And then we're going to talk a little bit about the Triangle tools and products that are involved with this product or with this project. 61850 is a collection of standards. It's built a stack of protocols so that we can have the different components and how they interrelate to build a complete communications infrastructure and data modeling. This is an overall view of the core parts of 61850. Our implementation here in orange is in this case, our PV inverter controller. A number of the basic parts of the standard come into play to make this project work. We have concrete mapping called a schism. This is what gives us the information about how 61850 maps to MMS, which is the wireline protocol used underneath. That comes out of part 8.1 in the standard. Above that here we have part 7.2, which is the abstract communication services layer. 61850 is based on using existing technologies as much as possible and separating those technologies out in order to future-proof. So 7.2 gives us the abstract communications requirements. The 8.1 gives us the concrete requirements, and so that wireline mapping can be replaced in the future as technology evolves. On top of the communication services, then we have the data models. The data models start with common data classes that collect the data attributes, the actual information in the device, into structures of data. Those are defined in 7.3. And then we have 7.4, which groups those data objects from the common data classes into what's called logical nodes. The logical nodes are the small building blocks of functionality in 61850. We'll look at a few of those shortly. Those logical nodes create logical devices and up into IEDs. There's a couple other parts here. 7.1 gives some overview of the background principles of all this, and other parts that give background information. But these are the core parts that build up the communications and modeling information. And then all of that information about the device and the systems is described in a language called system configuration language. It's provided or described in IEC 61850-6. We'll be looking at that and how the device is described in a few minutes. This is a quick overview of the client server architecture. In a later webinar, we'll be talking about multicast protocols used in 61850. Today we're focused on the client server perspective. In this case, we've got a physical device, which is our PV inverter. Our PV inverter provides read-write access from the client. It can also be configured to generate reports based on specific events in the device and communicate that information back to the client. So the physical device, in this case, we're implementing a photovoltaic inverter. This IED can also be a battery inverter, charging station, wind plant, windmill, or several other types of intelligent devices used in the DER space. On the client side over here in our demonstration here, we're going to use Test Suite Pro, Triangle's test client for the client interface, but in a production system, this could be an ADMS interface, could be microgrid controller, could be a control center HMI. That's the general client functionality. And a quick overview of the Triangle products that are involved in this project. SCL Navigator is our SCL editor. It has two primary functionalities. We're going to go through today a little bit about how we create an ICD file for a device. ICD is a IED capabilities description. A device that comes from a manufacturer needs to provide this file. It's a template file that explains the data model and the services available, the capabilities of the raw devices that comes from the factory. The vendors need to provide that file, so that STL Navigator's primary purpose is to ease that process, help guide vendors through creating that ICD file. It also has a functionality as a SCL verifier. We find that SCL files are not always perfect. SCL is an exchange format. One of the core tenets of 61850 is interoperability, so that we have devices and tools from different vendors that are able to interoperate with each other. To enable that, the SCL files are all often passed between devices and tools of different vendors. And if there's any question about whether the file is valid or not, that can waste some time and money as folks figure out which side of who's responsible for any issues there. So we find that having a third-party tool that can verify those files against the standard helps everybody be more efficient. So those are the two main functions of Navigator. We're also going to look at Test Suite Pro very quickly. DT is going to use that later in the demonstration to interrogate, interact with the device under test here, the PV inverter controller. So I'm going to go quickly over the highlights of that tool. And then, of course, we have our source code libraries, which are the foundation underneath all the Triangle products. In this example, in the PV inverter controller here, we're using the TMW ANSI-C stack. DT will go in a little more detail on that. We provide that compilable on virtually any platform imaginable. We also have C++ and .NET wrappers on top of that library available for more specific applications. So now we'll go quickly into Test Suite Pro. This, like I said, is our diagnostic test client. It's designed to help, first of all, our library customers implement devices, test the devices, and make sure they're compliant to the standard. It's also provides a lot of functionality for helping system integrators and end users, utilities, and in this case, DER system integrators, diagnose problems in the system, high-level communication issues, modeling issues, and so forth. So I'll quickly go through the main features of the tool. Here we have a Goose tracker. We're going to go through Goose in a later webinar, but this monitors the signals on the line and compares them to that SCL file, the system configuration description file we have, and would highlight if the packets we see on the wire are not what we expect from the configuration file. We've got a tool here for comparing models. This SCL is good. We need to have that to know what we're doing, but there are times a device doesn't get updated as it should. We end up with a outdated SCL file somehow. This tool quickly lets us attach to the device and compare what the device exposes online to what the SCL file tells us it should be. Saves a lot of time and confusion if there is any discrepancy in the files being used. We have some other tools here that help identify what's going on in the system from a testing perspective. There's some advanced test features built into 61850 that we provide some nice interfaces to. And then we go down and we have what we call the advanced client. This is a very low-level interface, allows advanced users to get in and interrogate the device in a fairly low-level way. We allow just about anything to be done here because the device vendors need to do negative testing. This does allow, in a lot of cases, violations of the standard to test the device against. So in this one, this is a very raw interface. We've also got Goose Publisher, again, for some of the test features in 61850. A test tool can publish Goose streams directly. There are ways to tell the devices to interpret test data, simulated Goose messages instead of the messages coming from the devices in the system. This supports that. And we do have an IED simulator in here. We're not using it in this example, but TSP will allow you to simulate an IED. In some cases, that's helpful to prove out the system and verify what we need. On the right-hand side here, we've got a couple of different display options that can help see what's going on in the system. In this case, we've got a demo example that's got 5 IEDs out there running bay controllers, breakers and disconnectors, and our CTs and VTs. This custom display allows a drag and drop of objects to quickly build a simple HMI as you design test cases and need repeatable situations. We can build a quick interface here to see what's going on. We've got a signal flow analyzer. We can drag data out of the data model set up dynamic displays here. As events happen in the system, we can track those in real time. Similarly, there's a logic analyzer that allows that data to be placed and viewed easily. We got use viewers and report viewers over here that allow for seeing the communications on the wire. So again, Dipthi will look at this a little bit more in the demo, but that's the highlights of that product. Then we're going to move into SCL Navigator. SCL Navigator is our SCL editor. And we do have the verifier. We're going to focus a little bit on how the model created. For the PV inverter, you put together a data model based on IEC 61850-7-420, which is recently published edition 2 of that, has become the basis for data modeling in the DER space, not only in 61850, but 1547, 20.30.5, and a number of other protocols in the DER space that have concluded that a harmonized data model is good for everyone. So based on that, we'll look at the completed file in a little bit, but we're going to go into quickly how to build this file. So I come up here, my file menu. I'm going to create a new file. And I'm going to create an edition 2 file. So I'll just select that for a new file. I need a file name. This brings me up a little dialog box that lets me preset some basic information about the file. There's a file ID. It's an arbitrary string related to the product. And we have a vendor name and software version number. And then we have a setting here to determine how we want to view analog values generally. 61850 provides for analog values to be represented as floating point numbers or as integer numbers. This talking about the exchange of the data on the wire. In most cases, we want that to be a float. There are two exceptions to that. We still have smaller devices in the field. It's possible to run 61850 on a processor that's not capable of floating point math. So in that case, we can use integer representations. And also sampled values typically uses integer representations for efficiency. But we can select these at any analog value in the model, but this lets us set the default for most cases in the model. So starting that brings up our template file here. This is about the simplest IED description we can come up with. We've got the STL header, we've got a little bit of a communication section. We really don't have that in ICD, but there's a stub for it here. And then the IED section. The IED section indicates the services that are provided by the IED. And this is a good starting point. These are typical services that an IED provides. This can be edited here as needed for the particular device, but this is a good starting point. Then under each IED, we have an access point. An access point's basically your Ethernet interface, and under each access point, we can have a server. And then, as I mentioned in the overview of the standard, we get into the logical devices and logical nodes. These are our data structures. They're fairly arbitrary constructs to organize the data that we need in our device, but they are standardized in 7.4 and 7.3 and 7.4.20 and so on. A logical device is required to have an LN0. LN0 collects the system data for 61850, our control blocks for communications, and some other information that applies to the whole logical device. Our IED has to have one LPHD. LPHD represents the information about the physical device of the system, nameplates and that sort of information. So we pre-populate that. That's required for the device here. And so this is our basic minimum set for an IED. SCL is constructed of data type templates. So we've got templates down here that build up these two logical nodes. This is all the information we need to find those. We start with our L node types, our data object types. Our data objects are constructed of data attributes, and those get down into our are constructed of basic types from 7 to our booleans and enums and so forth. So that's how all that's constructed. For the most part, Navigator relieves you of having to worry about data type templates, but it's important to know they're there. Sometimes you have to think about how to make the best use of them. So once we have our basic model here, we have an LN library. This is the parts from the standard. And so this comes with the different models. The LNs are broken up into groups designated by the first letter of the LN. Group N are measurement units. In this case, we're going to go back to part 7.4 for the basic logical nodes. We're going to start in this device with an MMXU. MMXU is the most common measurement unit. So this is how we provide information about the currents and voltages and so forth in the system. So to build the file, I just drag this over to my LN, my logical device, I'm sorry, drop it on my LD. I get this dialog box. This brings us up, adding new instance of MMXU. We don't have any in our model yet. If we had any in our model, we could reuse the templates and that would show up in a list here, but we don't have that, so we've got to build it from the standard. We can have a prefix, application-specific prefix on the logical node, completely user-dependent. The instance attaches to each instance of an LN class. The tool tracks that for us, gets us a 1 there. By default, we'll get a 2 if we start to do another one. Again, the analog type definition, we can override the setting we put here. Once we do that, we then bring up a list of all the data objects available in the MMXU. We've pre-selected the ones that are mandatory from the standard, and there aren't many. The MMXU can provide an awful lot of different information. Typically, we're going to see current and phase voltage in one of these, so I'm going to go ahead and select those. And that puts those two data objects in our model. Each of those is built from a CDC class, a common data class. And so I could further click into here and I can customize the data attributes that are optional in the common data class for each of these. I'm going to go ahead and go with the defaults here. We typically go through and be a little more rigorous in selecting those. And then I finish and I have an MMXU type. I'm going to go ahead and throw in one more thing. We've also got some protection equipment in this inverter. We have a PTOV, I believe. And this is a protection of time over voltage protection unit. So we drop that in. We have the same ability here to customize the optional components of this. And we allow it there. We've got a couple other tools available in here. We're going to stop adding now and look at examine our device. This is going to encourage me to enter history. I'm going to ignore that for now. We have a tool called Model View. As this is built up from these data type templates, it can be difficult to visualize what the model will look like online. So this window builds up the model view from those templates, assembles all that, and presents us a view of what a client will see when it connects to this server. Very helpful to the engineer to be able to see easily what's going on there. And we got a navigation pane so we can go through here. We have a lot of features in the model to navigate back and forth around these templates. As I select an LN, I can quickly navigate to the template. I can find the components that make it up, find what I need to do there. If I need any instance data in a model, the model structure comes out of those type templates, but if I need to pre-configure anything in here, I have a tool that adds the instance data here, as we have to build out the whole tree. And if I need to come in here and add any information in my model, for instance, a nameplate, I can come in here, my vendor, say this belongs to NREL. And once I fill in a value, then I need to strip all that extra information out, or all the unused fields out, because we have a motivation SCL that's expected to be as compact as possible. So we don't want any additional file size that we don't need. So we can come in here and delete all this unused instance data. So that makes it very easy to add the pieces we need in here and get rid of the pieces we don't. That's very difficult to do in a text editor. So the other tool we talked about and run through quickly, the SCL verifier. This is the tool that just analyzed the file we have here, and it goes through and tells us, this is telling me that I skipped that history indication, the dialog box that popped up, and I said I wasn't going to do. I should have done it, and it caught me. That's what verifier is for. We've got a couple little warnings down here because our file is nowhere near complete. It's telling us that I said this device will do reports, but I don't have any report control blocks configured. Same for logging and Goose. This is the tool that helps us verify files as they come through. So that's what that looks like. So those are the highlights of that. Dee will show us a little bit about the model she built with it here in a few minutes. If there's anything else, if you want any more information on either of those tools in the library, please reach out to Triangle. I think we have some questions now.
Normally, I would take a break now for questions, but we're good on questions right now and a little tight on time. So I'm going to go ahead and switch it over to DP. DP, let's go ahead and share your screen so we can get into your part of the demo. Okay, DP, you should have the screen now.
Yes. Can you see my screen back for the presentation?
Yep.
Great. Hi everyone. Today I will be presenting a use case where we have used the IEC 61850 server that runs on a Beagle board to show how we can use that to connect to a PV inverter. Let me go to the next slide. For this setup, we will be using a Beagle microcontroller, which we chose because it has a similar form factor and compute power as a lot of the PV inverter controllers that are available. And our development environment basically consists of a Linux subsystem on Windows. We'll be using a Linux host. We will also need a cross compiler and a GCC compiler if you want to compile for the host, and cross compiler if you want to compile for the BeagleBoard target. And we will be using the TNW's IEC 61850 source code library for this application. And we will also use the TestSuite Pro, which will be used to simulate the IEC 61850 client or the distribution system operator. And then we will also use the SCL Navigator in order to edit the ICD file in order to create a mapping between the server and the ICD files. So for the TNW source code, you can download this from Triangle MicroWorks website. It has instructions on how to unpack and set up the environment. The only requirement is that we do need the GCC compiler to run the examples. And the source code also comes with a set of makefiles for different architectures, like Joel mentioned. So you can run it on Linux systems, Windows systems, 32-bit, 64-bit, all of that. As long as you use the right makefiles for your application, it should be good. The use case that we will be looking at today is an IEC 61850 server, and we will show how you can get voltage and current measurements, and then a simple example where you can send out multiple volt-var curves where you can update it, and how the total var changes based on your curves. There are 5 steps that we need to go through in order to develop an application. The first one would be the ICD file development. Just opening the SCL Navigator here to go over the ICD file. As Joel mentioned, we're using the SCL Navigator to create this file. As you can see, for a PV inverter, we have these multiple logical devices that we've added in here. There's one for protection, measurement, for write-through curves, and then also volt-var, and frequency watt curves. So in this example, we're just going to go over a simple volt-var curve and how we can do the mapping for this. We use something called the S address in order to map between the ICD file and the server code that we would be developing. So you can go into the volt-var curve and then add something with a prefix. So I'm using the prefix FA in this case. You can use any other prefix. You just have to make sure that it maps to the source code as well. And once you have that set here, you can then go to the next step where you would define these S addresses within the source code itself. So in our case here, we're actually calling it the float array. So the volt-var curves are just arrays that have floating point numbers. So we can define them in here. And the third step would be how to actually map the data type that you just defined in here. For that step, we would be looking at, there's something called a demo or primitive XML file where you can define newer data types that you would be using. So here we are defining what the float array would do. You need to define 5 different handlers for any new data type that you declare. The first one would be the read handler, which basically which gets triggered every time a read instruction is done on the particular parameter. And then there is the write handler, which handles any write instructions that the parameter receives. Then there's the attribute handler, which just tells it what type of an attribute this is, and evaluation handler, which lets you validate if it's the right value and within bounds. And then you have an index handler, which is basically just used to index the S addresses in your source code. So once you define that within the primitives.xml file, you can then define the actual source code for all of these handlers within the file itself. So I have a really simple handler for the float array, since I only have volt-var in here. Just showing an example where this function gets called when a value gets returned to the volt-var curve. So you can see that we can get the index from the pointer to index handler, and then we should be able to get the volt-var curves as well, and just printing out what the current volt-var curves are. And once you have that value, you can use that value to perform your application within your code. Over here, I'm just changing the global var value, which is just the var value for this based on the curves that I get. I just check to see the X for the voltage is within a certain bound, and if it is, I multiply that by the var value, and this is what I do. This just shows another example that is available where you can take a look at that. Once we have the application ready, we would need to compile the code for the host, and then you can cross-compile it for the microcontroller as well. If you are going to be using the host for this, you would just use your GCC compiler. If you would like to cross-compile it for an ARM architecture microcontroller, you can use the GNU ARM compiler for this. So the compiler makefiles come with the option to choose either of these, so that we don't have to go and select them ourselves. This is an example of the compiler makefile that we have in here that comes shipped with the source code library itself, wherein you can go in and edit if you're going to be using a compiler or cross-compiler, if you want to use GCC, or if you want to use the Clang compiler. And you can also add paths to other libraries that your application needs in this makefile. For example, if you wanted ZMQ, JSON, anything, all of those libraries can be added in here. So this takes care of compiling the source code and then integrating that with the application code that you have. So once that is done, we can move on to actually launching the code on the host or the microcontroller. The one thing to keep in mind is we will be using networking ports, so it is good to have root privileges so you can have access to the Ethernet ports on the device itself. Let me go over this. Over here, I just have the tester pro that is connected to the server code, where you can go in here and try to connect it. And then within the advanced client, if you go in there, it should show you what is connected and not. And you can then select the inverter function, which is where the volt-var curves actually live. And you have the ability to change these curves. So for example, I can go in and change one of my curves to have a different value, which should change the bar value in here. Apologize for my computer being a little bit slow. So you can see how the bar value basically changes based on updating the curves. When our voltage is 120, we're within the range of between 0.93 and 0.95. And then when it falls into that, we just use that as a multiplier and we can change this. So we are using the client-server architecture in order to do this. And I think and later, once we would cover the other messaging patterns that we can use. But overall, you can also do other things with what we have in here. I'm also going to show an example of what is running in here. So you can see my volt-var curve basically updates with whatever value I give it. Initially with 0.1, and you can see what happens to the bar. All of that gets updated on the server side, and that gets sent back to the reporting. So the reporting basically tells you what is the latest value when there is a change, and it also tells you if everything is within bounds, and it is also timestamped. So you can use that in your application as well. Okay. And that's it. So you can launch your applications and try this out. Any questions? Thank you.
Thank you, DP. Right now, we're good on questions and I'm caught up there. So I'm going to go ahead and change the presenter back over to Kumar. So you can do your technical wrap up and have some closing comments.
Thank you, DP. Thanks. Good. Can you see my screen?
Yep, we're good.
Okay, sounds good. Yeah. So these are our other webinars that we gave in IEEE Smart Cities and IEEE Smart Grid newsletter, and we have a technical report on this, which is available in open source. So please feel free to go through these technical reports and newsletters. and let us know if there are any questions.
Okay, yeah, and if you can keep it on this slide, Kumar, I can just wrap up with some of the final thoughts here. So this webinar will be posted on trianglemicroworks.com. It'll be there on the homepage in about a week. We also do publish it on our YouTube channel. Everyone that attended will get a follow-up email with a link to this recording. You can also find the download evaluation licenses on trianglemicroworks.com for the tools you saw here today, for Navigator as well as Test Suite Pro. And then, Kumar, I don't know if we want to spend a couple of minutes on just talking about, if you want to collaborate with NREL going forward for future projects. I know our contact information is here.
Yeah, I do want to talk, 30 to 40 seconds on, on the follow-on work. I think PV inverters are definitely evolving, every day, and the next generation of PV inverters, I think they'll have grid farming capabilities. So what we presented here today is, based on the inverter that we built 3 years ago, which is a grid following inverter. But going forward, there's going to be more grid farming inverters, and we need to, understand how to have interoperability for them. The needs for grid farming inverters will be different, like exchanging peer-to-peer comms, high-speed comms between grid farming inverters, or even grid farming and grid following inverters. So we may have to use other fancier communications like sample values or goose messaging to make sure that they understand what's happening in the system. So definitely there is going to be a lot of follow-on work, and we are more than happy to work with industry members, universities, or anyone interested in this. So please reach out to us. And some of our work are in open source, so we can share part of this. And again, but I think it will have to go through Triangle MicroWorks. But we are more than happy to share any information that we can on our work to anyone who needs it.
Okay. Yeah, and as I mentioned, our contact information is there, Kumar and myself, if anyone is interested in working on some future projects. And this PowerPoint will actually go out to the attendees. Kumar had a slide prior to this one that had several links to different reports and articles and webinars. So you will get those links in your inbox shortly. There are also 2 handouts that are available to you on this webinar. You should see that in your toolbar. One of those is a product overview of Triangle's products. But there's also a download of the actual technical report. So you do have access to that for joining. So again, I do appreciate everyone's time. All the information is available on the different websites you're seeing here. We do hope to hear from some of you if you're interested in future projects. I will open it up to questions and answers if you don't have anything else, Kumar or DP, that you wanted to share. I think we do have 1 or 2 questions. Before
I covered what I want to cover. So yeah, we can go into questions, and please feel free to ask more questions if you have. We're more than happy to answer them.
Yep, so if anyone wants to start to enter in some questions online, we will be on for a minute or 2. I'm gonna just read off the first one here, and I'll open it up to the group. Is there a possibility to use LNs from with the BeagleBone? And I'm specifically referring to addition to logical nodes.
I think this is a question probably for Deepti or Joel.
Yeah, definitely. The model in the BeagleBone is constructed of logical devices and logical nodes.
Okay. I do have another question here. Historically, have there been any issues with security related to SCADA, such as Stuxnet malware or similar malware attacks? Have there been concerns related to security or not so much? Not sure if this falls a little bit outside this topic, but I'll open that up to the group.
Security is definitely a growing concern. I'm not aware of any malware attacks such as Stuxnet, but there are the occasional minor. I don't know that hacks is the right term. We had a water system in Florida attacked 2 years ago, I want to say. course, we're probably all, well, at least in the US, familiar with the Colonial Pipeline incident this year. So there are a few. We're certainly taking a closer look at it every day. I'm involved with the standards organization that creates the security protocols around 61850, 62351 out of Working Group 15. Handles those using TLS and certificates and encryption and authentication. All that's layered on top of 61850. It's definitely a lot of concerns, a lot of work going into how to secure these devices, especially as we get into DER. 61850 traditionally is inside the substation where you're counting on an air gap network. DER is bringing those issues to the forefront as we start deploying this out in the field. Marty, do you have any thoughts on that?
No, I would have to say, some of the security issues are beyond my, expertise. So yeah, I think you covered it pretty well.
Okay. Okay, well, we don't have any other questions coming in, so I think we're ready to wrap everything up. Again, thanks everyone for your time. Look for a follow-up email with the recording and the presentation so you can access those links. Please take advantage of the handouts that are available to you and downloading some evals from our website, and look forward to seeing you at the next webinar. Okay, thanks everyone.
Thanks everybody, have a good day.